Welcome students, and in this video we are going to continue our study of first order equations. So let's look at another example. Yes, so first example for today, example 1, we will consider this equation which is given by this y minus u times ux plus u minus x times uy equals to x minus y. And along with that, see, we know how to solve this sort of problem, but the thing is now we are going to put some initial conditions. So what is our data? So data is with the condition that we want u to be 0 on xy equals to 1. So basically xy equals to 1 is this hyperbola, and in that hyperbola we want our solution u to be 0. Clear? Okay, so now how do we find it out? See, what is happening is, first of all, we know that we can talk about the characteristic equation. So let's do that. The characteristic equations are, if you remember, it will be dx by this first coefficient, which is y minus u, and then dy by u minus x, and then du by x minus y. Okay, those are the equations. Yes, and of course you can write all of this in terms of parameterization. So the parameterized form, basically, let me again write it. So you can do either this the first part, this part, the earlier this one, or you can also write it as a parametric equation. So the parametric forms of this equation forms are this. So either one of them, you can write it in terms of this, the first one, or you can write it in terms of a parametric one. So the parametric one, what is it? It is basically dx by dt is nothing but y minus u, and dy by dt is nothing but u minus x, and du by dt is nothing but x minus y. Okay, now one second. Yes, this is fine. Now you see, if you want to write it down, all of these equations, I mean, note that this is true, right? See, this is nothing but, this is basically x dot. Yeah, I can write it like this. This is just a notation. This is again y dot, and this is u dot, right? This is just a notation. Yeah, but anyway, I mean, in this whole theory we can also interchange this sort of notations. Yeah, but essentially what we have is this. If you look at it, it is dt by dx plus dy by dt plus du by dt is 0. See, I mean, if you add all of these three up, it's going to be 0. Clear? And what does that imply? It implies that d dt of, since this is linear, right, x plus y plus u is nothing, is actually 0. So it means that this whole, whatever is there, this particular term, these terms are independent of t, right? So that will imply x plus y plus u, okay, or maybe I can just do it like this. Yeah, it's fine, it's fine. Yeah, this is equals to 0. I hope this is clear. Sorry, this is equals to constant. Yeah, because this okay, it is equals to constant. It can be 0, but basically let's just write it as constant, which is, let's just C1. Yes, and also note that this is also true. You see, x dx dt, okay, plus y dy dt. See, essentially this sort of problem, you have to make these small observations, okay, how to make your life easy. So this is one of those. First of all, you observe this one, and then you also observe this one. So if this is true, that will imply d dt of x square plus y square plus u square is equals to 0, which will imply x square plus y square plus u square is another constant. Let's just call it C2. Is it okay? Now, see, what we have is this. So we have this Cauchy data, right? So this data generally is called the Cauchy data. Cauchy data. Yeah. Okay. So if we use the Cauchy data, what you have is this. See, C1 of square is x plus y square, right? Yes, you see, x plus y plus u is C1. So you can write it like this. which is equals to x square plus y square plus 2xy. Okay, which is nothing but c2 plus 2. Clear? Okay, see, the data is xy equals to 1 on u equals to 0 on xy equals to 1. So basically, if we put xy equals to 1 here, then u is going to be 0. So basically, x plus y turns out to be just x plus y. Okay, so c1 square is c2 plus 3. Since u equals to 0 on xy equals to 1 on this hyperbola. Clear? Now, if this is true, then from here what do you get? Therefore, the integral surface is given by x plus y plus u square. Clear? And that will be equals to x square plus y square plus u square. Okay, plus 2. Yes, I'm just putting together all of this. See, c1's one second. You see, x plus y plus u is c1, x square plus y square plus u square equals to c2, and c1 and c2, c1 square equals to c2 plus 2. So we just write all of them together. Okay, c1 is x plus y plus u, and so c1 square is this equals to c2 is x square plus y square plus u square plus 2. Yes. Okay, so this is the thing. And of course, if you want, you can just write down u from here. Yeah. Okay, so therefore the solution is given by u of xy. Yeah, you can easily find u of xy. See, if you expand this thing, this is x square plus y square plus u square, which gets cancelled out here with these terms. Okay, and then you have this 2ux, 2uy, those terms are there. So you can just write it like this: 1 minus xy by x plus y. Okay, so simplifying, you get u, and that is going to be your answer. Okay, you can easily check it also. You see, if this u is your solution, right, and what happens at the point on the hyperbola xy equals to 1, this actually u turns out to be 0. So it actually satisfies the Cauchy data. Of course, you can also calculate ux and uy, and you can put it in the equation and see that this is going to be a solution. Of course, this is also continuously differentiable, so absolutely no issues here. Clear? So this is how you solve the equation. Okay, so maybe what we can do is, maybe we can start with another equation, and I will show you just another one so that it becomes very clear how to work out these problems. Okay, and maybe I can use a little complicated equation. It may look easy, but it's basically a complicated equation. So equation 2. Okay, see, this equation, if you look at it, this is example of a quasi-linear equation. Quasi-linear, because the coefficient depends on u. Quasi-linear. Okay, and again we are also going to look at the another equation, which is a quasi-linear equation. So the question, let's say if you are posed that you have to find the integral equation, so find an integral equation, integral surface, okay, of the equation. Remember integral surface, right? Basically the solution function, the graph of the solution function essentially. It is ux plus uy equals to 1. Yes. So essentially what happens is, you have is a simple equation which is given by ux plus uy equals to 1. Yes. Now the thing is this. See, this is the equation which the surface satisfies. And the surface, and it is also given that the surface passes through. Okay, the initial curve which is parametrized by by x equals to x naught of s, y equals to y naught of s, and z equals to z naught of s. Clear? So you understand. See, basically what we are trying to do is, think of it like this. So we are trying to find a surface, integral surface, right? And this surface, what is the speciality of it? Essentially, this is the so basically this equation, if you solve the equation, you will get some u, right? And that u is nothing but the that u is from xy, so essentially a subset of R2 to R, right? So if you look at the graph of that function, that is going to be in R3, yes, which is actually a surface. And since this equation is a first order equation, the solution which you are going to get is continuously differentiable. Okay, so essentially the integral surface which you are going to get is smooth, so it is basically continuously differentiable. Now, once you get it, what you have is this. So we want that solution in such a way that it passes. So basically there is this curve, initial curve. Integral surface should contain that curve, and that is our initial curve where we start our generation of this surface. Okay, right. So therefore the characteristic equation for the give R, this we know, right? What is it? This is dx by u dy by 1 dx by 1. Yes, and of course you can write it in terms of parameterization and in parametric form. They are given by dx dt, okay, equals to u, dy dt equals to 1, and dx dt equals to 1. Okay, so see, this is the parametric curve, you understand? Yes, and the thing is this is the integral curve. Essentially this actually represents the integral curve. Okay, integral curve. And what's happening is this: we are given that at the initial data. So basically what happens is, this is initial curve, right? Now you see this, let's say, for every point in this curve, so initial curve is given to you. What is it? This is x naught of s, y naught of s, z naught of s. Okay, and the thing is, this is for any s. So when s equals to 0, we start here, and after that we go this way. So that will be your parametric curve. Okay, so you see, if you go for every s, you do this thing, every x you go and do this, then you get this surface. You understand? This is how the surface is generated. So you are given his initial curve, right, which is given by x naught s, y naught s, and z naught s. So this will be z naught s. Sorry, I made a mistake. I think this should be z naught s. Some parametric curve is given, and the thing is this: what you want to do is this. See, essentially for every s, so this s, let's just assume that s lies between 0 and infinity or whatever, s lies in R, right? Or for now we can easily see, it does not really matter where we are choosing s from. So for now let's just assume that s starts from 0 and it goes to, let's say, some 1 or something. Yeah, it doesn't matter where. Okay, so what we are going to do is this. See, so this is s, right? As s moves, this curve moves. Yes, s moves, this curve moves. Okay, right. So you can think of this curve as some gamma from 0, 1 to R3. Clear? That's your initial curve, which is given by x naught s, y naught s, and z naught s. Now the point is this: if you fix a s, let's say s equals to s naught. Okay, and corresponding to that, you start, this is your initial point. So you start here, and after that you look at the integral curve which starts here. You understand? The integral curve starts here, and it actually moves along in the integral surface. Okay, again for another s1, let's say, we can do similar sort of thing. Yeah, so if you go on doing this thing, you understand, if you go on doing this thing, what happens is you actually end up getting a whole surface like this. That's the idea. Okay, I hope this is clear now. Okay, so you see what is happening here is this is the integral curve, and what are the initial data here given. Now you see this curve, if you think about it, this curve of course depends on t, but it also depends on s. S is the parameterization of this, of the initial curve. Okay, so this depends on, yes, 1 second. Yes, I did a small mistake here. 1 second. Maybe I can change it to u. I'm using u. Yes, so I can change it to u equals to u naught of s. It doesn't matter, something you have to write it, but anyways, and this also you have to write du dt. Yes, there's a small mistake. So you do realize that, see the integral curve. Yes, the integral curve, this is the integral curve, and it varies according to t. So basically this is a function of t, of course, but this is also a function of s if you think about it, both x, y and u. Why? Because for each fixed s the t varies. You understand? That gives you one integral curve. Now you see, if you vary s, then you get a family of integral curves which actually gives you your integral surface. Is it okay? So essentially here what's happening is this, we have to write it properly. So here the initial data, so we should write this like d dt of x of s and one second here, s of t. So x is a function of s and t. This is going to be u, or we can write it like this: d dt of y st is equals to 1, and then d dd of u st is equals to 1. Yeah, and there are initial data. What is the initial data? So what is the initial data says? You see, initial data says as x is x naught of s. Yeah, so it means that at t equals to 0. Yeah, so where it starts, see, t, as t evolves, one integral curve evolves. So basically at t equals to 0, this is the initial curve, right? So you see what happens is, this is given that at s t equals to 0, this is going to be x naught of s, that's given. Yeah, and y at the point s0, t equals to 0, yes, it is y naught of s, and z at the point s0 is z naught of s. Is it clear? Okay, so this is the total parametric curve given the initial data. Now, of course, you can solve this thing. Let's just solve it. This is x of s of tau. Let's just call it that this is tau square by 2 plus tau u naught of s plus x naught of s, if you solve this problem, right? And then y of s tau you are similarly going to get is tau plus y naught of s. And then similarly z of s tau, what you are going to get is tau plus u naught of s. Yeah, just by solving this problem. You see, this is a this thing ODE, this is a system of ODE, right? And the initial data is given. So basically think of s as fixed for now. For a fixed s, this is true, and then this is a family. So there is a two parameter family, s and tau. Okay. Now you see, so these actually gives you the whole, parameterization. Yes, so you see, since this is two parameters, yes, essentially this actually gives you the whole integral curve. Yeah, okay. So what we do is now, so you can of course leave it here. You do realize that a surface can be parameterized using two parameter, and if you just do this parameterization, this is more than enough for the problem. Okay, but the thing is, for better understanding of what's happening here, let me put some initial data here. Yeah, now. Set a particular, so let's say a particular set of values. See, the problem is done here. It is done. Huh? What I am going to do here is this. So you can leave it here. So essentially, see, we are looking for an integral surface. What is an integral surface? So any surface you can actually write out in terms of two parameters. So here, x, y, z, you already have this function as a two parameter family. So this is actually a surface. But the thing is, we are again going to do it using a particular, example, so that it gets clear. A particular set of values of initial data, okay, let's put that data. So let's say x at the point s0, yeah, s0 is nothing but 2s square, okay, and y at the point s0 is nothing but 2s, and zu at the point s0. So basically t equals to 0 is where the integral curve starts. Clear? S0, and s is positive. Clear? Okay. So now with these initial data, this is just a random initial data, nothing special happening here. If you put all this together, it becomes s of x of st is nothing but half tau square plus 2a square. Clear? And y of st, similarly you are going to get as tau plus 2 times s. Z of st, similarly you are going to get as tau, sorry, u of st. I keep on writing z, but we used a u here, so it is tau. Yeah. Now you see, you can eliminate tau and s here. If you eliminate tau and s, eliminating tau and s, you are going to get a surface which is purely in a Cartesian form. So basically what you are going to get is u minus y square plus u square equals to 2x. This is what you are going to get. Okay. Now you see, you do realize that the surface, you see the solution surface, what is the, now of course you can, I mean, if you want you can just break it up and you write it like this: 2u equals to y plus minus 4x minus y square whole power half. Of course you can do that. Now you see, on y square equals to 2x, u equals to 0, that data is given. See, this is what, u equals to 0 on y square equals to 2x, right? So, and it satisfies this thing. Yeah. Now, please remember this thing. See, there is this term whole power half. So, this is not the surface we are talking about. So, what I am trying to suggest is this. For some problems, it is better to leave it as it is, like this parameterization. Now, if you are asked to find the exact Cartesian form of that, then you have to write it like this. But in this case, you see, 4x square minus y square can't be negative, right? Yes. So, what we can do is this. We have to do some more analysis. So, you see, this represents, yeah, this formula. This represents a surface. Surface is solution surface. Surface. If y square is less than 4x, right? See, if y square is less than 4x, so basically 4x minus y square is positive, then only it represents the solution surface, right? And the solution for when y square greater than 4x, the solution does not exist, and of course they are not differentiable at y square equals to 4x. So for y square greater than 4x, it does not exist. Of course, in the real variable does not exist. And when y square equals to 4x, it's not differentiable. It is not differentiable. Okay. So you see, what we can do here is then you can just write it down that what the solution is. In this case, if y square equals to 4x, I mean, if you look at that particular region, we in that upper half region, 2u equals to y plus minus 4x minus y square whole power half is going to be your solution. Is it okay? So I am going to leave it here. Yes. So let's leave it here. Yeah, I hope you understand what's happening. If you write down in terms of this, it may happen that in some region it may not be satisfied. So what you do is you actually find out what the region is where it is satisfied, and then you are done. Okay, right. So that's your solution thing. Yeah, I hope this is clear. So now what we are going to do is look at a very, very important part, which is called a canonical form. Canonical form of first order linear equation. Okay, so what does canonical form mean? See, canonical means what is the core form of it. Okay, think of it like this. So basically linear equation. So basically what we are trying to achieve here is this. See, let's say you are given an equation which does not look, looks very complicated, right? Very big. Yeah. So for example, a general equation first order will look like this, right? Axy ux plus bxy uy plus cxyu plus cxy times u equals to dxy. This is the equation which is given to us, right? Yes. And you see, what we need to do is this. We want to put it in a standard form. You understand? Yeah. So let's call it star. Yeah. So this is a complicated equation. And of course, let's just assume that a, b, c, d, all of these are continuously differentiable. Absolutely no issues. You can just assume that. See. Okay. Now, what we want to do is we want to simplify this form in such a way that is very easily integrated and that sort of thing. You understand? So, what we are going to do is see, this is in this. So, basically, if we want to change it into a simple form, what you can do is essentially we can take a new transformation. So, basically, change a variable. This is in xy, coordinates, right? What we do is we change the coordinate in such a way that this becomes very simple. So, what we do is this. See, first of all, we introduce the new set of coordinates, new transformations. So what are those? Let's just do that. Transformations that is given by xi equals to xi of xy, okay, and eta equals to eta of x comma y. So those are the new set of transformations. Of course, here we are assuming xi and eta are C1 continuously differentiable, and the Jacobian, yes, of xi and eta. So let me write it down what it means. So basically it means that xi x eta y minus eta x xi y. Okay, that's the Jacobian. This Jacobian is non-zero. Okay, in whatever domain we are interested in. So let's say we are interested here in omega. So then it will be in omega. Is true? Omega is of course subset of R2. Yes, we are just doing it in R2. Please understand that. Okay. So if you do that, therefore, by chain rule, what happens? By chain rule, maybe I can give you an example of what we are trying to do here. So let's say initially we have this equation, the equation in xy, right? Now let's say for as an example, so this is nothing to do with the problem. This is an example of what is exactly happening. What is this transformation? So let's say you define xi of xy to be x plus y, okay, and eta of xy. So what is the Jacobian matrix in this case? It is xi x eta y. Xi x is 1, eta y is 0, minus eta x. Eta x is 1 and xi y is 1. So it is minus 1, which is not equals to 0. So this transformation is valid. You understand? Yeah. So this is how we have to look at it. So this is basically this sort of thing we are doing. This is just an example, but to make it clear. Now with this new coordinates, you see the equation will change, right? So essentially what's happening here is this: u of x in this case can be written as u xi x plus u eta x, and u of y can be written as u xi y plus u eta y. Clear? Clear? This is just a chain rule, nothing special is happening. Yes. Okay, so once this is true, you see we can replace this ux and uy in star. So replacing in star, we can actually have a much easier problem. So it will look like this: a times u xi plus b times u eta plus c u equals to d. So this is the modified form where a is given by u xi x plus b xi y, and b is given by a eta x plus b eta y. Yes. Now you see, if you understand what's happening. See, essentially we don't know what xi and eta is. The equation is given to, we don't know. So basically what we know is we are trying to find a xi and eta which are continuously differentiable so the Jacobian is non-zero. So if that is happening, ux and uy can be written like this. If these are written like this and then you put it in the equation, the modified equation in terms of xi and eta looks like this. Yeah, where a and b are this. Now you see that, let's call this 1. Now from 1, okay, if b equals to 0, so let's say that, see, this xi and eta is on our hands. We want to find that xi and eta. So you see, b equals to 0 if eta is a solution of a eta x plus b eta y equals to 0. You understand? See, if I am choosing a eta in such a way that a eta x plus b eta y equals to 0, I can choose that. Once I do that, then that will give me b equals to 0. Yes? Okay. So, you see, and this equation again is a first order equation. We know what to do with that, right? And there are like infinitely many solutions. Yeah. And so what we do is this. So you put all this, I mean, you can choose any one of them. It's absolutely no issue such that the Jacobian is non-zero. Yes. Okay. So once you do that, what happens is, so choosing one such eta, choosing one such eta. You understand? This equation, we can easily solve it, right? And there are like infinitely many solutions of eta. You choose one eta such that the Jacobian is not 0. That's how you do it, yeah? Okay. So, you see, if you do that, then this equation becomes u eta, u xi, sorry, plus alpha, one second, yes, plus c by a times u equals to b by a. Yes, yeah, fine. Okay, so since b is 0, we actually can reduce it like this. Now you see, this equation is much easier to solve. You see, yeah, and this is called the canonical form. This is called canonical form of a, form of 1. So you understand what's happening, right? You just choose one eta in such a way that this becomes 0, and then the whole equation turns out to be a much easier equation to solve. Okay. Okay. So with that in mind, let's just solve one problem, and then we will have a very good idea of what's exactly happening here. For example, so let's say ux minus uy equals to u. Yeah. We want to just solve this equation. Yeah. We want to find the canonical form of this equation. Yes. Of course, you can do this. I mean, this is a very simple equation. Of course, you can do your usual thing. Yes. But let's just find out in canonical form. In canonical form, we want to find out what is the canonical form of this. Canonical form. Yes. See here, if you write down the characteristic equation is dx by 1 equals to dy by minus 1 equals to du by, okay, and the characteristic curves are given by, so you do it in similar way only. Yeah, how to find xi and eta. The question is how to find xi and eta. I will show you how to find it. So here also you do this characteristic equation thing. Yes. Okay, once you do that, you see the characteristic curves. Therefore the characteristic curves are x plus y equals to c1 and y equals to c2. Okay, those are the characteristic curves. C1 and C2 are constant. Therefore, choose xi of xy to be x plus y. Okay, so we are choosing xi in such a way that xi is constant along the characteristic. You see, xi is this function. So if you are restricting xi to the characteristic curve, you see in characteristic curve is x plus y equals to c1. So basically xi becomes constant c1 on the characteristic curve, and you choose eta also in such a way that it becomes constant on the characteristic curve. So let's say eta, we choose it to be y. So y is c2. So essentially eta is also constant along characteristic. Yeah. So if you do that, then what happens to ux? Ux is u xi x. See, u xi x plus u eta x. Yeah. So you just calculate all this thing. What will happen is ux equals to u xi and uy equals to u xi plus u eta. Okay. And therefore, the equation which you are going to get, you see, this is u xi. The canonical form is u xi, right? So basically, it becomes ux becomes u xi minus uy. Okay. So uy is u xi plus u eta. Okay. That is uy. So this is equals to u. Yeah. So that will actually give you u eta equals to u. Okay. U xi, one second. Let me just check it once. ux minus u xi plus u eta. Yes, so this is, sorry, this is a minus u eta. Yes, this is fine. Yes, okay. So this is your solution. Now, of course, I mean, you do realize, you see, solving this equation and solving this equation is very, very different. This is a very, very simple equation. You can just solve it, right? And you can solve it. You can write it like, what is u of xy? This is going to be f of some xi e to the power minus eta kind of thing, right? Yeah. So, and you are done. Yeah. It's very easy, this equation. So you understand canonical form. The point is this: you somehow have to find xi and eta. How do you find xi and eta? You write down the characteristic curve, and using the characteristic curve. So basically what you do is this, I mean, choose xi and eta, choose, generally speaking, xi and eta in such a way that they are constants along the characteristic, constants along the characteristics. Okay, so basically we choose xi and eta from here, looking at the characteristic curve. So once we do that, now you have I mean, reduce it to ux and uy, and you put the value of ux and uy, then you are going to get your simplified version, which here it looks like this. And of course you can easily solve it. You solve it and you get, this is your solution. Okay, so this is the way you solve these equations and find out solutions, by making it in a much simpler form. So by reducing it in a much simpler form. Here, so with this we are going to end this video.